Alright, for number 1, you had the Seattle Great Wheel, and you had to answer a question. Create a diagram that shows the position of a passenger car on the Great Wheel as it rotates counterclockwise at 45-degree intervals. And this is all you had to show here for that. These are the 45-degree intervals for that problem. And for the solution on this, it went as far as to cut that in half, the 175, and make it 87.5. So that is the radius of 87.5, and then it goes negative back here, positive here, negative there. Which you did not have to do. You could have just marked it off like that. For part B of that problem, on the same set of axes, sketch graphs of the height and co-height functions for a passenger car starting at the 3 o'clock position on the Great Wheel and completing one turn. Okay, so the blue curve represents the height function. That is the distance from the x-axis up to the passenger car, and you can see that it starts at 0 and makes its way up to 87.5. And then it's coming down the other side, and it's even again at the 180 position, and then down at the bottom at 270, and then back up for one complete turn at 360. And notice how that's different from the co-height function, which is in red, which I'll overlay in purple. For the co-height function, you're looking at the distance from the car over to the y-axis, so it's 87.5, and it gets closer as it gets to 90 degrees, and it's right on it, so it's 0. Then we're going back around to 180, and it's further away, but it's in the negative value. Down to 170, it's right on the y-axis again, and then back around to the starting position. Discuss the similarities and differences between the graph of the height function and the graph of the co-height function. And these are things that will hold true throughout whatever comparisons you make in a different problem. Both the height and the co-height functions have the same domain. You're going from 0 degrees to 360. And the range is negative 87.5 to 87.5. And this is for that particular problem. Both functions have the same maximum value, 87.5, and same minimum value of negative 87.5. But they occur at different amounts of rotation. That's what you should take away from that. And explain how you can identify the radius of the wheel from either graph. Well, the radius of the wheel is the distance from the center of the wheel to a point on the wheel, wherever that may be. So you can easily measure this at one of the 4 points when the car is at the top or the bottom of the wheel, or at the far left or at the far right. Alright, for number 2, in 2014, the high roller Ferris wheel opened in Las Vegas, dwarfing the Seattle Great Wheel, with a diameter of 520 feet. If the diameter is 520 feet, then that means that the radius would have to be 260 feet. Sketch the graphs of the height and co-height functions for one complete turn of the high roller. So if you have the height as being the height from the x-axis up to the passenger car, starting at the 3 o'clock position, then clearly you're going to be at 0 to start with. But notice on this graph that it goes up to 520 at 90 degrees. And then when you get to 180, it's back to 0. And then when you go down to here, it's at negative 520. And then back up here to 0. Can you think of any reason why that it's marked off at 520 instead of 260? Did any of you mark it off at 260? So as we discussed in the last class, for some reason the key for this has taken this up to 520. as if it were the height. Like the Ferris wheel has a radius of 520, and that is not what was given in the problem. So either in this question on the key that word is wrong, or they've made the wrong graph to illustrate what was being asked. So if you went up to 260, that's still fine. And the same thing with the co-height function. Notice that they've taken the distance, the starting distance for the co-height from the car to the y-axis, it's at 520. It should be 260 with what we've been doing. But if your graph is going to have essentially the same shape, it's just going to be at different measurements. So we'll leave that one as it is, as long as you know the reason why yours looks different than this. All right, number 3, consider a Ferris wheel with a 50-foot radius. So this one has actually expressed a 50-foot radius. We will track the height and co-height of the passenger cars that begin at the 3 o'clock position. Sketch the graphs of the height and co-height functions for the following scenarios. So for A, a passenger car on the Ferris wheel completes one turn. So naturally, if it's a 50-foot radius, the height would start at 0 at the horizontal axis, go up to 50, and then back to 0 at 180 for a half a turn, and then back up here too, after it dips down back to 360 degrees at 0. And then the co-height starts at 50. It's that far away from the y-axis. It's right on it at 90. It's away from it at 180. It's right on it at 270, and then back away from it at 50-foot intervals. And then for section B, the passenger car completes 2 full turns, so it's the same thing except you extend it out further. And notice that it goes 360 degrees and then to 390, 420, 450 would be the same as being at 90 degrees, and so on. It's just 2 complete turns for each one. It's not that major of a deal. And then for part C, the Ferris wheel is stuck in reverse, and a passenger car on the Ferris wheel completes 2 full clockwise turns. So you're going the opposite direction. So you start at 0, but then you end up in the negative territory at the what is essentially 90 degrees, but it could be 270 as well if you're going in reverse. And it's going to follow the same pattern, except it's just coming down. And then for the co-height, you're still 50 away, but you're going down, and then back up, down, and then back up. And then for part 4, consider a Ferris wheel with a radius of 40 feet that is rotating counterclockwise. At which amounts of rotation are the values of the height and co-height functions equal? So the thing to take away from it is this. Consider the right triangle formed by the spoke of the wheel connecting the car to the center and the horizontal axis. It's talking about this, where you have your car here, you have the center of the circle there, and then you're drawing your height there. This is the horizontal axis there. The position that you need to concern yourself with, and that if you followed it around the wheel, you would have noticed that these spots would occur at 45, 45, 90 triangles. So your first one is at 45, the other one is at 135, and then you're coming down to 225, and then over at 315. Those create 45, 45, 90 triangles, where your height and the co-height are going to be equal. This would represent the co-height, this would represent the height. Legs of a 45, 45, 90 triangle are equal, so therefore the height and the co-height would be equal there. Alright, so number 5, the last one. Yuki is on a passenger car of a Ferris wheel at the 3 o'clock position. The wheel rotates 135 degrees counterclockwise and gets stuck. Lee argues that she can compute the value of the co-height of Yuki's car if she is given one of the 2 following pieces of information: the value of the height function or the diameter of the Ferris wheel. Is Lee correct? And the short answer is yes, but you have to explain how you know. Here is how you know. and it's similar to the last answer. If you're stuck at 135 degrees, you have created a 45, 45, 90 triangle. And of those two pieces of information, the diameter or the value of the height function of the car, if you have the height function here, then you're going to know the co-height function there. Because it's a 45, 45, 90 triangle, the height and the co-height would be equal. We just went over that in the last problem. So if Lee knows the diameter of the wheel, then she knows the radius, which is half the diameter. Then she knows the length of a leg, which is square root of 2 over 2. And that just goes back to geometry, which you had last year in most cases. The objectives for today are the same as they were yesterday. I'm not going to read through them, but I've recorded enough of this to where you could pause it later and take note of that if you want to. Today's entire lesson is about the motion of the moon, sun, and stars, and most specifically the motion of the sun as it relates to ancient times when we did not know as much about astronomy as we do today. We know certain things today, back then they did not. We are going to use what they knew back then to make certain calculations. So in general, just for an opening, why does it look like the sun moves across the sky? What answer can you give to that? The rotation of the earth is what's making it look like the sun moves across the sky. And a more formal answer is that the sun is essentially still, not really, it moves as well, but the earth rotates on an axis every 24 hours, so we're moving, it makes it look like the sun is going across the sky. Is the sun moving or are you moving? Technically both, but the sun moves imperceptibly, which means you can't notice it, while an observer on the face of the earth rotates away from the sun. In ancient Greek mythology, here we go, just like I warned you, the god Helios was the personification of the sun. He rode across the sky every day in his chariot led by 4 horses. Why do your answers make it believable that in ancient times, put yourself back then, people imagined that the sun was pulled across the sky each day? The technical answer is if we did not know that the earth rotated every day, then a reasonable explanation would be that the sun moved across the sky each day. Keep in mind that in those times the earth was also flat, according to them. So that's where it came from. Now in mathematics, counterclockwise rotation is considered to be the positive rotation, which runs counter to our experience, which is a clock, unless it's digital. Of our experience. Is there a connection between counterclockwise motion being considered to be positive and the naming of quadrants on a standard coordinate system? So take a look at this. If this is considered the positive direction in math, remember that on the XY coordinate plane, this is quadrant 1, this is 2, this is 3, and this is 4. That is why it was named that way. And since we're going to be talking about the sun, notice that you have the sun here, the earth here, a distance to the sun, and an angle of elevation there for the sun. And from that we will be looking at the height of the sun as it was in ancient times, and so on. So the short answer is yes, and we made that diagram. What does the circle's radius represent in this diagram here? The distance between the center of the earth and the sun. We went over that. Now, how has the motion of the sun influenced the development of math? The naming of quadrants and the idea of measuring rotations counterclockwise in a sense, in terms of how we perceive motion of stars and planets. And then how is measuring the height of the sun like measuring the Ferris wheel of a passenger car, which we've already gone through? Both situations relate a vertical distance to a measurement of the rotation from an initial reference point. So that's how that ties into what we've already done. In this section, here comes the strange names. We discuss the historical terms used by Aryabhata the first in his astronomical work that led to trigonometry. So Indian names are spelled phonetically in the Roman alphabet, so Aryabhata is Aryabhata. And the best known work of Aryabhata is a compilation of mathematical and astronomical results that was not only used to support new developments in math in India and Greece, but also provides us with a snapshot of what was known at the time. Ergo, the chariot pulling the sun across the sky. And we're going to use his developments to model that motion just like we did a passenger car on the Ferris wheel. So think of an arc of a circle. Here's a piece of a circle, and here is the arc. The Sanskrit word for bowstring is samastaja. Indian mathematicians often use the half chord ardhaja, so that Aryabhata used the abbreviation ja for half the length of the chord joining the endpoints. So here is the chord joining the endpoints. He used the word ja for half of that, and look what happens when you go through there. You have created a triangle with an angle theta, and he named that piece ja. And it's a right triangle. We're going to use that in relation to the sun being here, the earth being there, and then the R value, which will come up in just a second, is a constant value that you use with any of this stuff to still come up with the same measurements. The term kodaja, often abbreviated as koja, which is what we're going to use, means the side of a right triangle. So here's what we just did. We had ja there, we had the radius, we have the earth, we have the sun, and now we have koja here. So when you see this name and this name, do not be alarmed. Beware that ja is relating to the height, and then koja is the other leg of that right triangle, which would be the horizontal distance from the earth to where the sun is over top of. Indian astronomers used a value of R, a constant value, kind of like we use pi as 3.14, and the constant E that we used in the financial problems of 2.71 and so on. R is going to be 3438, a distance from the earth to the sun, so that we can calculate the height, which is ja. And this came from a circle whose circumference is 360 degrees, which is 360 times 60 minutes. That's 21,600 minutes. Minutes in the mathematical sense, which we don't need to know right now. So here is a formal setup of what we just went through. He used an arc, and the endpoints of that arc were connected. He cut it in half and came up with this, which we already drew, and this. This is the height, and you can think of this as the co-height. Can you see how that plays into that word, co and co? And then, of course, the constant value of R. Here's the earth, and here's the sun. Where this comes from, there is a table I will give to you. And this table is sectioned off in terms of 3 3/4 degrees. And it comes from this recursive formula here, which I have zoomed for you, such that S1, which is item 1, is 225. And then if you add 1 to that n, you're getting a new degree measurement. You're adding 3 3/4 degrees to it. And you can add all of those up, is what this means. Each of these in there, adding those up, dividing by the 225, subtracting from the general n plus S1. You don't need to know all of that, but this is where it came from. So in this table, here's what we're going to do. We're going to calculate Ja at 7.5 degrees, which is right there. And then Ja 11.25 degrees, 15, 18 3/4. That's the first thing that we're going to do. And I've already set these up on separate screens, so there's not a lot of zooming and anything going on. So what we're looking at first is this, the 7.5 degrees for theta. And here is the diagram for that so that you can see where it came from. Here is theta, 7.5 degrees. We are looking for Ja, which is this. What is Ja in relation to 7.5 degrees? Is it adjacent, opposite, or hypotenuse? It is opposite because it is straight across from it. And the R value of 3438 is on the adjacent side or the hypotenuse? Hypotenuse. Remember, this is a right triangle. Hypotenuse is opposite of the right angle. So we're using which trigonometric function to solve for Ja? Sine. So sine of 7.5 degrees equals Ja, which I've just labeled X, over the constant of 3438. And when you do that in your calculator, you must do sine of 7.5 first, and then multiply by the 3438 constant. And that comes from cross multiplication here. Round your answer to the nearest whole number, the nearest one, and you should come up with 449. So that was simple enough to fill in your table there. Use the same process to find Ja at 11 and 1/4 degrees. So you would do sine 11.25, enter, and multiply by 3438. What do you get? 671, yeah, so you can fill that in on the table. And Ja at 15 degrees, sine 15, enter, times 3438. What do you come up with? 890, yeah. Ja at 18 3/4 degrees, so sine 18.75, enter, times 3438. What do you come up with? 1105, right. So there's what we found in the table. 449, 671, 890, and 1105. Now look at this. Here is the column here in which you can abbreviate this stuff. Instead of going through all of this, the third column in the table simply shows you that, for instance, if you did this one, Ja of 7.5, that all you had to do was 3438 times sine of 7.5. And do you come up with 449? Whoops, I put it in the wrong spot, my fault. 449. You still come up with the same thing. So that just illustrates the shortcut. So you do not have to fill in the whole table. What you get from this is the shortcut is this. Radius 3438 times sine theta will give you Ja. That is the main point to obtain from this. So now label the angle theta, jaw, and cojaw, and r in the diagram below. And I've done that for you, and we already did that before, so there's no need to copy that again. And how does that relate to something that you've done before? Well, the sides of a right triangle. They are also like the height and co-height functions of a Ferris wheel. So if you look at this, you have the height function and then the co-height function there for the legs of the triangle. That is where that came from. And here's what we came up with from the table. Jaw is the same thing as coming up with r times sine theta. And if you wanted to find cojaw, which is the same thing as the co-height function, it is the same as r times cosine theta. Because remember, cojaw or co-height was at the bottom of the triangle, and that side is adjacent to the angle we had. So here it is at the bottom, like this. And remember that cojaw here is down there, and that's adjacent to theta. That's why you're using cosine in that case. So these are two abbreviated formulas that you can use to find those deals whenever you need to. And that can also apply to the Ferris wheel whenever you have an instance that comes up like that. All right. So use your calculator to compute r sine theta for each value of theta in the table from exercise 1 where r equals 3438. But we've started doing this similarly before, where we've already found this value there, where you do 3438 times sine theta, and we noticed that they came out to be the same thing. So there's no need for us to go through and do all of that. Now here is an example that will come in handy, and this is the following. We will assume that the sun rises at 6 a.m., is directly overhead at noon, and sets at 6 p.m. We measure the height of the sun by finding its vertical distance from the horizontal line, that is jaw in the ancient times. The horizontal line that connects the easternmost point where the sun rises to the westernmost point where the sun sets. In other words, that's the x-axis. So in here, what I'm going to do is draw a triangle, or not a triangle, but a circle that has a fill of white and an outline of black. And let's see how good this goes. Not bad. Maybe a little shorter. This is supposed to be the x-axis, and there is the y-axis. Now we know that the sun rises at 6 a.m. in the east. And the problem told us that at 12 noon it's directly overhead, and that the sun is going to set at 6 p.m., so it must be sometime in the winter or close to it. Look at this table. You have the sun rising there, and then you have 1, 2, 3, 4, 5, 6 different items up to and including when it's directly overhead at noon. So look over here in your circle. You have 1, 2, 3, 4, 5, and then 6, including the 12 p.m. Can you see how that would be 7 a.m., 8 a.m., 9 a.m., 10 a.m., and I've left no room for 11 a.m., so I'll just cheat and do that. And for some reason I drew an H, so we'll just make it 11 a.m. There we go. So see how at 6 a.m. the sun has not risen. It's starting to, but it has not risen yet. What is the height of the sun at 6 a.m.? 0, yeah, so we'll go in and put a 0. And now at 7 a.m., here we are at 7 a.m. If we have 6 markings up to and including 12 p.m., which of course 12 p.m. is what degree measurement? 90. And if it takes me 6 markings to reach 90, then how many degrees is 7 a.m.? 15 degrees. 90 divided by 6 is 15. So we know that this is 15 degrees, so we put that in there. Remember the shortcut for finding the height, which was ja in the other problem? It was ja at theta degrees equals r times sine theta. That was the shortcut. And remember, in this problem we have to use the r value of 3438 from the ancient times. So if we perform that calculation, we can do sine of 15 degrees and then multiply it by 3438. What is the height of the sun at 7 a.m.? 890. Okay, so 890. Use that same thing for 8 a.m., except 8 a.m. is now what degree measurement? 30. So you would do sine 30 and then multiply by 3438. What is the height of the sun? 1719. What is 9 a.m.? What degree measurement? 45. So you can do sine 45 and then multiply it by 3438. What is the height of the sun? 2431. So, and we don't need to fill out the rest of that table. You get the point. Today, this isn't ancient times. For some, it might be. For others, it is not. But the R value now we know is approximately 93 million miles from here to the sun. So if I use this same process to find the height, which is ja, of the sun in the sky, then it would still be 0 at 6 a.m. at the sunrise. But if we use the 15 degree marking and do sine of 15 degrees, and multiply that by the true distance of the sun, 93 million miles, then you would come up with approximately 24 million miles. And if you were to round that, you could make that 24.1 million miles. And you could do the same thing for the rest of that table using 93 million miles. And I've already finished the table for you for the R value of 3438. And if you went ahead and finished that out just out of curiosity, there are the answers. As well as for this table here, for the 93 million miles, it comes out to be 24.1 million like we found. And then we have 46.5 million. 65.8 million, and so on. And you get that from r sine theta.